So, now Pedro presents us about shadows and gravitational lensing of Einstein-Friedberg-Lee-Sirlin boson stars.
So, good afternoon. My name is Pedro, and I will present the oral communication entitled Shadow and Gravitational Lensing of Einstein-Friedberg-Lee-Sirlin boson stars. Here's the summary of my presentation, in which I will start by the introduction, speaking a little bit about the model and what is the action that we need to solve in order to find the usual the EFLS space, the EFLS solutions, and then find the usual geodesics in this space-time and the astrophysical images of such object, ending up by the final remarks. So, starting by the introduction, as we have seen a lot in this symposium, boson stars are an example of non-topological solitons, and they are often referred as black hole mimickers. In this context, the Einstein-Friedberg-Lee-Sirlin model can be utilized to study field configurations influenced by gravity in more realistic theories with symmetry breaking potentials. So, in order to find a solution of EFLS boson star, we need to start by the action given in equation 1, in which the Lagrangian for the matter field is given in equation 2, where the potential is now given by the equation 3. In this action, the phi field, scalar field, is the complex scalar field, and the psi is the real scalar field. Both of them being coupled by a coupling constant m. A really interesting feature about this model is that as we vary the mass parameter associated to the real scalar field mu to infinity, the real scalar field tends to its vacuum expectation value, which turns out to turn the EFLS theory to recovers the Einstein-Klein-Gordon model. If you take the action 1 and vary it with respect to the metric and both the scalar fields, the complex one, the real one, we are able to obtain the field equations given from 5 to 7. In order to find a spherically symmetric solution, we of course have to impose spherically symmetric ansatz both for the metric, which is given by the line element in equation 8, and the real and the complex scalar fields, which are given in equation 9. In order to make the computations more simple, we also do a rescaling given in equation 10. So after that, we substitute these ansatz, these spherically symmetric ansatz, in the field equations, and then we obtain the ordinary differential equations, which we solve utilizing boundary conditions that ensure regularity at the origin and asymptotically flatness. After that, we obtain the solutions, and then we are able to compute not only the solutions, but also some attributes associated with those solutions. In this table, I show you 4 different solutions named FLS1 to FLS4, in which we show the parameters mu, omega, m, which is the mass of the specific solution, the number of light rings, and the location of the external light ring of the given solution. As we can see here, it's possible to have in this theory, specifically the FLS2 and FLS4, solutions with light rings, which always comes in pairs. And to show the next results, we choose specifically in this table the solution FLS1 and FLS4. So in order to obtain the geodesics and the light rays in this spacetime, we have to solve the geodesic equation. And after doing so, we are able to obtain, for example, the result given here in the first figure. As we can see, the solution FLS1, which is, we're coming back, the solution with no light rings, does not have a gravitational lensing effect strong enough to make the light rays turn around the solution, which is located at the center of the image, which is not the case of the solution of the FLS4 solution, where we also have the presence of light rings, and then the light rays being able to turn around this star multiple times and be scattered in different angles, bigger and different angles. So we can move to the astrophysical images of the EFLS stars. And in order to obtain the image of a Eiffel star, we have to impose some sort of light source, which is in this case the accretion disk, and then we impose the model of an accretion disk that will be surrounded the boson star, and this accretion disk will emit some light and will interact with the curved space-time created by the star, and then we will be able to capture the measure intensity, and then okay, and then obtain the astrophysical images of those objects. The the accretion disk model is then can then be, we have to solve the geodesic equations together with the radiative transfer equation given in equation 9, in which I Ni, J Ni, and alpha Ni are respectively the specific intensity, the emission coefficient, and the absorption coefficient. And all these parameters are associated with invariant parameters given in equation 12, where nu is the frequency of the emission of the light ray emitted. So we choose to work only with with light rays which are monochromatic, and this is given by in the equation 13, in which we have this Dirac function selecting only the specific frequency we're working with, and in this case we also choose the emission profile given by equation 14. In this context, utilizing the invariant quantities that I just showed before, we're able to obtain the expression that will tell us what is the relation between the intensity emitted by the accretion disk and the intensity measured by the observer, which is given by equation 15, and where nu prime is the observed frequency. In this context, we also choose the FLS1, FLS4 solutions to show here. And as we can see, the solution FLS1 does not have a gravitational lensing effect strong enough to have the same features as the FLS4 solution, which is a solution that possesses light rings, as we showed before. And both these images are being observed from at the angle of 80 degrees. A really interesting thing that I have to mention is that the accretion disk, in this case, is a thick accretion disk, which means that it's opaque. So the light rays do not cross, are not able to cross the disk multiple times. And then we have these patterns of figures. We also are able to compute the same images, but now locating the observer in an observational angle of 5 degrees, which turns out to make the observer look at the images from, let's say, above. And still we can see some differences in this image regarding the intensity of intensity of the intensity of the observed intensity of the accretion disk. So we also compute those solutions for the case of a thin accretion disk, which means now that the light rays are able to cross the accretion disk multiple times. They are not stopped by the presence of the accretion disk, and this changed the features of the solutions FLS1 and FLS4 that chosen for this presentation. This turns out to change the features. So the FLS1 still not solution that bend the lights as the solution FLS4, and for that reason the FLS4 shows many more features in the image, where we can not only see the light rays that come from below the star, but also we can see a signature that reveals the presence of the light ring. We also can see that signature in the image observed from the angle of 5 degrees, which is an interesting result and can somehow distinguish this solution from others with different parameters and even black holes. So we've reached the final remarks, and in resume, we see that the chosen FLS star in this presented here can support the presence of light rings. The photon rings in optically thin disks are a key signature to distinguish them from black holes. And compact EFLS star can mimic black hole shadows under certain conditions, such as the chosen model of the accretion disk, the compactness of the star, and other features. So this is my acknowledgements and references. Thank you very much.
So we have time for questions. People.
Thank you. Very nice presentation. I was wondering, so how did you model the accretion disk? You say is a geometrically thin accretion disk, right?
Yes.
So it's a like quasi-geodesic flow around the star.
Yeah, it's a flow of matter field, but it's a rather simple model based on these works of Rosa and Sengo.
Okay. And how the sorry, maybe in the previous slide, can you go? Okay, so here you got the intensity, emission coefficient, and all the rest. Like, how does this relates with the parameters of the null geodesics that you because you do some sort of ray tracing, right?
Yes.
Yeah. So was wondering whether the parameters of the geodesics somehow will appear in will be related to this intensity, emission, and absorption coefficient, right?
Yes. So most of the computation we choose the accretion disk, and this accretion disk does have a profile, and the intensity is measured. The intensity is measured by such profile. Okay, and what we do is we solve the geodesic equations until a point where this geodesic end up in a point of such profile. This profile is then we then mark the point where the geodesic turns, the geodesic end up, and then we compute this other quantity to see the Doppler effect, the gravitational effects, and just because the emitted intensity is not the same as the observed intensity, you see.
Okay.
So it's some sort we kind of do a map where the light ray will from where it comes, and then we see in which region this corresponds to the profile we are looking at, and then we utilize this expression to measure the Doppler effect and so on.
Okay, I see. Thank you very much.
You're welcome.
Oh,
I think you cannot ask.
Just a comment. We do not solve the hydrodynamic equations here. We can do that from the zero, solve the hydrodynamic equations and and see what's the for velocity of the fluid. But we just impose it in a built-in model, the model that was already in the literature for the intensity. Yeah, more phenomenological, exactly. We are not solving the hydrodynamic equation. We can do that, solve the hydrodynamic equations and see what's the distribution, the stories around the boson star, for instance, and see what's the emissivity. But we choose to impose the model for the emissivity and see what's the image that the star generates.
Yes. It's a rather simple model. We don't. Yes.
any further questions? So I actually have a question. I mean, about whether this can mimic or not a black hole. It mimics a black hole when it does have a light ray. Is it correct?
Yes,
So
it have to be compact enough to somehow be comparable with a black hole.
right. So, but what I was asking myself is, well, a light ring has an event horizon. So, as it has an event horizon, it usually has only one light ring.
Yes.
And in the case of boson stars, you have the divergency at the origin of the effective potential. So if you assume you have a unstable light ring, you must have a stable light ring.
Yes.
And
As I just show here.
I was asking myself uh, if the presence of these stable light rings somehow is a barrier to the mimicking of black holes, because we expect that black holes have only one light ring. So if boson stars have light rings, then they must have at least two light rings.
Yes.
Doesn't this presence of an additional light ring modifies the astrophysical image?
Well, usually in the computations, the presence of the stable light ring do not allow us to see the coming light rays. You see, you can have some points in the boson star or in the older solutions where you have some sort of chaotic behavior, and then you see other patterns. But the signature that you will see here in these results are just because the unstable light ring allow us to see the light rays that have enough energy to escape back to the observer. You see?
Mhm. You can continue with it. That's the
Yeah, what I was about to say is that this is not something that we see as a behavior for the stable light ring.
right. Okay, so there is another thing that I would like to maybe comment, and that for me the question of if there is a light ring or there isn't a light ring is an important one. But another important question is whether there could be a light ring. So, like a general condition for the existence of a light ring. And there is a quite recently put forward conjecture by Svetic and Gibbons, which states that stable light rings occurs when either the strong or the dominant energy condition are violated. So maybe this is some sort of way of testing this conjecture, or given a result, a general rule for the existence of a light ring in boson stars. Because is there a result established that whether a given boson star will have a light ring? There is a rule of compactness or something like that?
What we usually do is to analyze the effective potential. So we look. There is also a topological explanation for that, but we also can look at the effective potential that describe the trajectory of light rays in such space-time and see if there is a minimum or a maximum. But that conjecture you just mentioned looks really interesting. I will look forward it.
So let's thank Pedro again.